Okay, it's time to start. And as usual, we got a little bit behind, so I'm going to cover some material that's you need to do your homework for today, but I think we'll be able to do it pretty easily, I hope. So let's just jump right in. Do you remember at the end of class last time, we had done the univ operator, right? Remember that? What it does? It takes apart, it enables you to access what? The functor and the list of arguments, okay? And you can do it on either side, you know. Okay, so we'll start our demo today with another predicate called functor. So the next built-in predicate that we want to look at is called functor, and here is the specification for it. It says if you say functor, it's three-ary, so it's term, functor, and arity. And the specification is functor, the middle one, is the functor of term, so that's term, and arity is its arity. And by arity we mean number of arguments. Are you with me? So let's just do a bunch of demos here. Let's do functor. Now we'll do F, and then we'll do A, B, C, D. And so that's, and what's the arity of functor itself? It's 3, right? So if we do capital F and capital N. Now can you predict, based on that specification, what's going to happen? What will big F match to? Little f, yeah, the functor. And what will big N be? What will it be instantiated to? 4, yeah, because that's the arity. Is everybody with me? Are we good? And so if we do functor, but now instead of doing that example, let's do G, and then let's do A and 5, and then we'll do F and N. So now predictions. F match G and N 2. Good. Okay, and how about this? Now, how about a prediction for this, you guys? T, G, 3. Huh? Huh? Anyone want to hazard a guess? I will give you a hint. This succeeds. How in the heck can this succeed?
G, parentheses, and like underscore.
Yeah, exactly. T is G with 3 arguments that anonymous, right? Are we good? And the next one we'll do is, let's do functor. We'll do a little more complicated one. We'll do T, parentheses, F, big X, and then big X and little t, paren, and we'll do fun. Call it fun this time, and arity. So questions about this? Predictions on this? Predictions? T, yeah, good. Yeah, fun will be T. And then what? Yeah, why not? Why the heck not? Okay, so now that's functor. Now another one that we have here is called arg. Arg. Okay, so arg n, term, argument. Argument, so the third parameter, is the nth argument in term left to right starting with 1. So that should be easy to predict. How about arg? So how about arg 2, and then F, and let's do A, B, C, D, E, whoops, comma, and then capital A. So now, so what will this be? A match, yeah, A will match with B. Good. Okay. And then how about arg2, and this time we'll do F, and we'll do capital X, and then T of A, Are you with me? And then T of B, yeah, and then capital Y. So what do you think about this? Why not? Excellent prediction. And how about this? Instead of this being A, suppose this is X. Prediction? I mean, why not? What's obvious? Yeah, why not? And then, but, I just did that to throw in an uninstantiated variable here. But now how about this? How about arg, actually here, let me go back. How about arg, and instead of saying 2, suppose we say n, and then we do f of a, b, c, d, e, and then we say we want that to be c. Now what would you hazard a guess here? What would you hazard a guess here? Yeah, you would hope that n would equal 3. But unfortunately, arg requires that n actually be an integer. So it doesn't go back, it doesn't count, do the processing to count.
Is it an error also because it's expecting the argument to be a variable also?
Oh, this? No, it could either succeed or fail. Oh, that's a really good question. Let's do another demo. Watch this. Let's suppose we do this. Is this 3? Anybody want to guess this one? I think this was what your question was, right? What do you suppose is going to happen here? Yeah, why not? Good question. That was not in my demo list of demos to do, but that was a good one. Is everybody good? Okay, so now let's take a look now at the topic of how to compare terms. Okay? So check this out. We started this whole unification thing with this match. Yeah? Match, single equals is match. So here's how here's a list of ways that we can compare terms. First, we can compare them by matching. And we've explored that in infinite detail. But now, another way to compare them is with equals equals. And now, with equals equals, it's different from matching. With equals equals, x and y are, what this means is x and y are identical. We'll see what identical means. We'll do some demos to see how x and y can be identical. And then x and y are not identical is bash equals equals operator. And then if you want to compare arithmetic values, so it's x equals colon equals y. So this x and y are arithmetically equal. So that we want to be able to compare numbers. So this is how we compare numbers, is with the colon, is with the equals colon equals. And then x and y are not arithmetically equal is equals bash equals y. And then we have a less than. So this is arithmetic less than. So x is less than y. We've used this before. And then we have equals or less than, greater than or equals. And then if you ever want to do alphabetic order, you use this ampersand less than. Okay, so we're going to run through demos of all these to see how they work. All right, so let's go back to our demo. So first of all, let's contrast matching. Let's contrast matching with identical. Okay, so now let's do a little review. So x match A. Prediction? Yes, and so they do compare. Yeah, so they do, x equals A, they do match, right? And how did this work? X match Y, where both of them are variables. Do you remember what happened here? Can two uninstantiation, let me start over. Do two uninstantiated variables match? Yeah. Some people are changing your mind on the fly here. Do you remember that they do match, right? That was one of the first things that we learned, yeah? Are we good? Two uninstantiated variables do match. Are you with me? Now let's contrast that with x equals is uninstantiated x identical to a? So what do you suppose? Correct, it is not, okay? But how about, how about x, uninstantiated x and uninstantiated y? What do you suppose is going to be the case here? Yeah, it's also not the same, right? They are not identical, okay? On the other hand, check this out. This might be a little, let's do x match a, and then let's do x equals a. Now, what was x identical to a before? It was no. But in this case, what have we done? We've instantiated it. Well, what happens is, this time, it's yes. So what is our conclusion here? Our conclusion is that if x has been instantiated, it uses the instantiated value to do the comparison. Are you with me? And how about this? Suppose we do x match a. Now, how about this? X match a, y match a, and then x equals y. X is identical to y. Now, what do you suppose here? Yes, because it uses the instantiated values. Okay, so the conclusion is equals uses the instantiated values for comparison. Uninstantiated variables must be identical for the comparison to succeed. Is everybody good with that? Okay, so now let's do some structures. Let's do f of a, b, and let's say equals f of a, b. So, I mean, what do you suppose should happen here? Now, this is not match, this is equals, but still, what do you suppose should happen? Yeah. Okay, and what do you suppose should happen now if we do this with this?
No.
And why are you predicting no?
They're not identical.
The x is not, yeah, if you did the b equals uninstantiated x, they would not be identical. Does everybody see how that works? So everything is consistent here. Are you with me? And then if we did the same thing here, oops. And now look, if we do this, let's have this be uninstantiated to a different variable. What do you think here? Now, by what we had said before, what should happen here? Yes or no? No. Correct. Okay, it should not, because we already saw that if we do y equals x, okay, that's no, because if they're both uninstantiated. Are we good? Now, how about this? X match y, and what's going to happen here? What's going to happen here? Oh, we just did it. What's going to happen here? We'll do it again. No. Okay, so now how about x not equals y? I mean, what do you suppose is going to happen? Yeah, if the first one fails, the second one succeeds. Are you with me? And vice versa, right? So how about x match a, and then x is not identical to a. What do you think? Good. So our conclusion is equals succeeds when bash equals fails, and not bash. Yeah, bash. When bash equals fails, and vice versa. Are we good? Now, what was the arithmetic comparison? What was that? Equals. So let's do a 3 equals 3. And what do you suppose? Why not? And how about if we do x match 3 and x equals 3? And so what do you suppose that? Why not? And how about this? X 3. Now, what kind of a comparison is this always? It's an arithmetic comparison. So can you guess the... Actually, it's even worse than a fail. It's even worse that they're not equal. It's an instantiation error. Does everybody see what happens? Okay. So our conclusion is that, you know, it has to be instantiated. Let's do one of those other comparisons. 4 is less than 7. So what happens here? Oh, that was pretty complicated. And 7 is less than 4? No. All right. And what was the alphabetic order? Remember the alphabetic order? At, right. Okay, so let's do bear at less than berry. So is bear less than berry alphabetically? It does it come first in alphabetic order or not? It does, because the B's are the same, the E's are the same, but the A is less than R in alphabetic order, so this does succeed. And just to show you, berry at less than bear. Oh, wait. Wait, bear. Oh, berry. I spelled berry wrong. That was a, okay. I need a spell checker on this thing. Okay. Are we good? All right. And now what we're going to do, using these new little tools that we have in our toolkit, what we're going to do is we're going to have a third version of count. Now, check this. We'll do these tests. We're going to do a third, remember how we did count and we counted the number of occurrences? But now watch this. We're going to have a third version of count, which is count 3. And do you remember when we did our first 2 versions of count? What would happen here? Do you remember what would happen here if we had A and then this was A, B, X, Y, A? Do you remember what our first version of count would do for this? It would do what? Yeah, it would instantiate X to A, and it would count A as how many? As 1, 2, 3. Here, it would be 4 times, right? But now, what our count 3 is going to do. So let's copy this. Oh, I already did. So now what this is going to do is this is only going to count 2 copies. I mean, okay. So if X and Y are uninstantiated, well, they're not the same. Are you with me? And then how about this? What do you think this should do if our... Yeah, it should be, this X should be equivalent, should be identical to only this X. And so N is 1, and there's no more solutions. And then just to compare that with our old version, maybe we should have done this one first. To contrast this with our old version of count, this one's going to be, 3. Oh, this isn't X, yeah. Actually, I think I said it wrong before. I was thinking XX. It's not XX, it's XY, right? So this is going to count, why is this going to count 3 for A? Because this X will get instantiated to the A, and then this X will be A. So that's why N is 3. Are we good? So now, do you see how to do count, our new version of count? Instead of using what? What did we use before? We used matching. So now all we got to do is what? Yeah, just do the is identical to, you know, the equals equals. So do you remember how we did that? So what's the base case? Right. And if the list is empty, it doesn't matter what the first argument is. The count is 0. Okay? And now what do we have to check? To see if the what? The first one. Yes, good. To see if it's the first one. So how do we see if it's the first one? Yeah, term, and then head L and N. So now yes, term, good, very good. So term equals head, and then we'll do a cut. Because if term is not equal head, then we won't do the cut, and we will backtrack. But if it is equal head, then we're not going to backtrack. So then what? Don't we have to do,
Count 3 term L.
yeah, I think we have to do count 3 on L and N. Is that right? Is that what you're saying?
We could do N1 and then N is N1 plus 1.
Exactly. And then N is everybody with me on this? And then N is N1 plus 1. And then I think we're going to, as I recall, this is with just one clause. So we're going to put the or here. I mean, one rule. Okay, and then, so now what do we do? N, yes, count 3 term ln. Right. Okay? Is everybody good? So there's our count 3. Now, the next topic is about, now this next one is really slick. I think you're going to like this next one. It's about asserting and retracting. So let's go back to the slides temporarily for this. Now, the one thing that we have to be aware, oops, I hit my microphone there. The one thing that we have to be aware of here is, with this assert and retract, is that there are some differences between G prologue and the prologue that's described in our textbook. Okay? So if you just go by what's in the book, you're going to be thrown off a little bit. Okay, in the first place, the predicates that that are described in the book, there's 4 of them. There's assert, and assert A, and assert Z, and retract. Okay? Now, the thing of it is that G prologue only has 3 of these 4. It doesn't have the first one. It only has assert A, assert Z, and retract. Okay? So that's the first thing you have to be aware of. So don't try, if you experiment with assert, it's not going to work. Now, and here's the, so that's, you just have to be aware of that. But here's the idea of the assert. What you can do in prologue, one of the things about artificial intelligence, what would you like to have a robot do? I mean, besides, clean the dishes, clear the table and clean the dishes and wash, I mean, what you want, for artificial intelligence, one of the things you want a robot to do is to learn. Right? So that means something in the database has to, as you acquire new information, what has to happen to the information in your brain, the information in the database? The information itself has to do what? Adapt and change. It has to change. All right? Now, up until now, this is really cool. Up until now, all of the facts and rules that we put in the database, once we put them in there and we consult, that's it. But in order for the database to evolve, the database itself to evolve, in order for the facts to evolve, and the database itself needs to be able to change. Are you with me? So assert A and assert Z are putting information in the database, and retract is taking information from the database. Now, and this is after we've done the consult and while we're doing the, as time progresses. Are you with me on this? So what happens is assert A adds at the beginning, and assert Z adds at the end, and remove removes. And the things that are getting added and removed are clauses. Yeah?
Does it actually put them in the file, or is it just adding them for this time while you're in G prologue?
For this time.
Okay, so it's not actually changing the file itself.
No, it's not saving the file. Right. There are ways to, but if you want to save the file, then there are ways to do that. Okay, but right now it's on the fly, so it's like it's in memory. So, but there's for sure there's ways to do that. Okay, but we're not gonna get into that. This is going to be on the fly. But you'll see there's some really cool demo. Our author has some really cool demos here. Okay, so now, you understand why there's not a retract A and a retract Z. I mean, because if you retract it, it's going to go find it and retract it wherever it is. But if you put it in, you want to be able to have the flexibility of putting it either at the beginning or at the end. Are you with me? Okay, so we're going to have assert A, assert Z, and retract is what gprolog. Now there's one other thing about gprolog that's different from what's in the book. In gprolog, we have to have, if we want a clause to be able to be asserted and retracted, we have to say at the beginning that it is dynamic. And the way you say that it is dynamic is you use this colon hyphen followed by dynamic. All right? And this also is not in the book. Okay? This is a gprolog way to do these asserts and retracts. Are you with me on that? And so I'll show you here in a minute, but just make sure. So if you want to have a clause in your database, you want to be able to add or remove it dynamically. That is, when you do a query, you must declare it to be dynamic in gprolog with this declaration. The compiler needs this designation when it consults your database. Okay? Now, here's the thing. You can add or remove any clause not already in your database without this designation. But if there are some clauses in there that you do want to add, to assert or delete, you have to state that they're dynamic. Are you with me? So that's, yeah? So these are efficiency considerations. Okay, now, so let's go back to our demo. Now, check this out. Let's see. Actually, what we'll do, I've already consulted ch6.po, which is this file up here. So now, check this out. What we have here are, and then here's some comments that we just went over on the slide. So we're going to define nice. Nice if what? Sunshine and what? Cannot prove it's raining. Wouldn't that be nice? If it were sunny and no rain. Okay, so that's nice. Okay. But that would really be funny if it were both what? Sunny, sunshine, and raining. Actually, that's when you get rainbows, but they're kind of rare. So that's kind of like funny conditions. Are you with me? Are we good? And then it's disgusting if it's what? When is it? Oh, it's disgusting outside. If it's raining and fog, I mean, like in London or whatever. Yeah? Are we good? Raining and fog. Does everybody agree? Now, there's nothing in here that's different from anything else that we've done before. We're just declaring nice if, sunshine, raining, funny, and these functors have arity 0, right? Okay, and now what we're doing is, now remember, I have consulted this. So now what you see, this is that gprolog thing. This colon hyphen dynamic sunshine arity 0, and dynamic, and then colon hyphen dynamic raining arity 0, and colon hyphen dynamic fog 0. So now, does everybody understand that these three things right here are the gprolog way of saying that if I have some sunshine and rain and fog in here, I want you to treat it dynamically when I consult. So now here are the facts in our database. Are you ready? What kind of a day is it? Raining, period, fog, period. Now, is everybody with me on this so far? We told Prolog that if we have raining and fog, that we want these to be dynamic. So it knows when we put it here that, oh, this might change during the queries. Are you with me? Is everybody good? Okay. Now, check this out. Let's do nice. Now, we'll go back here. What did we say? So if I do nice and I press return, what's it going to do? It's going to do what? Up here, what's it going to do? When I see nice, nice is going to match this nice. It's going to be nice if what? Sunshine. So then what's it going to do? It'll go back and go back to the start of our database and look for what? Sunshine. Okay, and here, is it going to find it? No. So what's going to happen if I do nice? Correct. Okay. How about disgusting? What's it going to say? it's going to say yes. Does everybody see how that's working? Are you with me? But now what happens if I retract fog? Now look, I retract fog without a period, right? So this fog here, I'm retracting, but I don't put the period inside here. Are you with me? So if I retract fog, what's it going to say? Oh, okay, yes, you retracted fog. Okay? And now what's going to happen when I say disgusting? No, because it's not in there anymore. So does everybody see what happened? It looks like it's there in the listing, but it's dynamic and we retracted it. Yeah, question?
If you consult the file again, does it protect the memory?
Yeah, it does. Yeah. Okay. And now, you guys, I want to put some sunshine in there. So how do I do that? Let's do assert Z and say sunshine. Okay, and now that I have asserted sunshine, and see, it says, oh, sunshine, that's going to be dynamic. The user might want to assert it sometime. So I did, we put it at the end, okay? And now, and furthermore, I want sunshine and we want what? No rain, so what do we do? Retract raining. Yes, you retract it. And now, is it nice? We made it nice. Oh, that's a good question about the order. Well, let's do an example. We have to remember what's in there now. What's in there now? Just sunshine? So let's do assert Z raining. Assert A. Does anyone want to guess or predict? It should still work. Okay. So now let's see. So is it nice? No. Are you with me? But is it funny? Yes. Okay. Actually, yeah. Is everybody good? Now, here's the thing. A set of clauses can be removed through backtracking. Now watch this. So look what we have here. We have dynamic fast and dynamic slow, right? Some people are fast and some people are slow. Ann is fast, Tom is slow, and so is Pat. Are we good so far? Is everybody with me? So fast, slow, they are dynamic, and we have in here fast and slow Tom, slow Pat. So if I say, let me see. So if I say, oh, wait, one more thing. What about faster? Okay. What about faster? Now watch this. We're going to assert Z. Now, we're not just going to put a fact in there. What are we going to assert? Not only can we assert facts, what are we going to assert? A rule. Are you with me? Now, why didn't I have to declare this to be dynamic? Do you remember from the slide? Why didn't I have to declare this to be dynamic? It's not originally in there. Faster is not originally in there. So therefore, we can, if it's a new one, we can assert it without pre-specifying it. Is everybody good? Okay, so that was a good observation. So now but now this is in there, right? Are you with me? This is in there. So here's the question. The question is, what happens if I say faster AB? What's it going to do? What's going to happen if we say faster AB? What's going to happen? Well, it's going to match XY, and so it's going to look for what? Fast X, and so it's going to find what? Fast N, all right? And then, so that's going to succeed, and then what's it going to do? Slow Y is going to find what? Tom, so it's going to be faster what? So it'll be what? X and Tom. But then, after, will there be more solutions? And the next solution will be and Pat. Is everybody clear on that, on how that worked? Okay, because we put that rule in there. But now watch this. Now what we're going to do is we're going to say retract slow X. Now, retract is non-deterministic. Now, what does non-deterministic mean with these queries? It means if there's more than one solution, it does the next one and the next one. Are you with me? So let's copy this and come here and do retract slow X. So what do you think is going to happen here? It's going to retract, it's going to match X with Tom, but then if I want another solution, it's going to do what? Match X with Pat. So now who's gone? Yeah, slow Tom and slow Pat are now no longer in there. Are you with me? So now if I say faster and anybody, is it going to succeed or fail? Correct. Then Pat would still be there. The slow Pat would still be there. Yeah, but I wanted the other solution. Or if I did A, you'd do, they would all. Is everybody clear on how that worked? Now here's a little demo of assert A versus assert Z. Okay, so watch this. If we do assert A, actually I'll tell you what, I think I'm going to let you do this. I think I'm going to let you do this on your own. This is just a demo to show that A and Z, to show the difference between assert A and assert Z. But I think we need to move along. And so if you want to, these notes are on the web page, and you can download it and try these tests to see how that works. But there's two other topics that we need to do. One is my product. This is the concept of memoization. Now, so first thing that we're going to do is let's take a look at my product, XYZP, and the definition of my product is, well, obviously, P is the product of X and Y. And so we say P is X times Y. So here, to demo my product, we can do it like this. My product, now watch this, 3, 4, and P. So obviously, what should this be? Yeah, P will match 12. Is everybody good? But now, what about this? Suppose I do my product, and I do 3, and I do X, and, oops, I do 3, and I do X, and here I do 12. Now, it would be nice, I mean, can you see what would happen? What's going to happen here because of the is? Instantiation error, right. Okay? Because is, up here, is needs to have these instantiated to do the multiplication. It does the arithmetic. Okay? But now, you guys, there's another approach to this. Okay? It's called, now, I always like to call this the Elmer Fudd. You guys know Elmer Fudd, he couldn't pronounce his O's. That wascally wabbit. So if Elmer Fudd were to say memorization, he would say memoization. Yeah? But this really is memoization. That Elmer Fudd. And it's also, and this is a well-known, computer software engineering term, this concept of memoization. It has to do with caching. And now what we're going to do is we're going to, there's this real slick demonstration of memoization. Instead of calling it my product, we're going to call it product. And product is going to have 3 things, X, Y, and P, right? Just like before. But what we're going to do is we're going to have this make table. Okay? And check out what this make table is. When I run make table, okay, first of all, product is dynamic, right? So if I run make table, it's going to be, what's it going to do? L is going to match what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The list. Are you with me? And then what? Remember, X and L. So that's going to succeed if what? If X is a member, so if X is what? 0, 1, 2, 3, 5, 6, 7, 8, or 9. Are you with me? And it'll do them with backtracking, all of them. Are you with me? Is everybody good? And then we're going to do what? So the first time X will succeed with, and X will succeed with instantiated to 0, right? Then it will, and then what will happen? Y will do what? Remember YL, so what will happen? Yeah, Y will succeed with instantiated to 0. Are you with me? And then what are we going to say? Z is X times Y, and then what are we going to do? We're going to assert Z what? Product what? 0, 0, 0. Are you with me? Product 0, 0, 0. And then what are we going to do? Then we're going to fail, because after we do fail, what's going to happen? We're going to backtrack to Y. And the next time Y will be what? So we will backtrack to Y, and the next time Y, remember YL will be what? Y will be what? Y will be what? 1. Okay, and so that will succeed. And then what will happen? Z is what? 0 times 1, and then what will we assert? Product what? 0, 1, 0. Product will be in there. It will be product parentheses 0, 0, 0. Product parentheses 0, 1, 0. Product parentheses blah, blah, blah. And furthermore, each time we go through, we fail, it'll backtrack until what happens? Remember all the possible members of Y and L and X and L, and so we'll have actually how many entries? We'll have how many product rules in the database? 100. Are you with me? Is everybody clear? Okay. So now let's run make table. Are you with me? Make table, period. Now watch what happens. No. Wait, why is it no? Because it always fails. But what's in there now? A whole 100 products. So now do you see if I do product, I don't know, give me some numbers. 4, 6, Z, what's going to happen? What's going to happen? Yeah, Z is 24, and that's it. But what's cool about this is the following. Now I can do what? I can do what? Product what? X, 6, 24. And now what's going to happen? 4. And that's the only solution. And not only that, we can do what? Product what? X, Y, and what? 24. And now what's going to happen? 3, 8, 4, 6, 6, 4, 8, 3. Is that cool? Because what? Because they've been memoized. You see? They've been memoed, they've been cached in that table. And so now, is that cool? That's an example of memoization. Now there's one more thing that we need to do for your homework tonight. And that is, we need to show bag of. So I hope we can do this in 5 minutes. All right. So now, to demo bag of, here is our data for our bag of tests. So now does everybody see what we have here is age, it's two-ary, and what does age Peter 7 obviously mean? The age of Peter is 7, the age of Anne is 5, the age of Pat is 8, the age of Tom is 5, and also the age of Henry is 5, and there's another Henry who's also 5. So there's another Henry who's also 5 years old. Are we good? So there's our age. So now let's do this with this in mind. Let's say let's say age child 5. Age child 5. So now, what should happen here? First, and then what? Another one, then another one, and then and Henry is twice. Is everybody good? Does everybody see how that works? Okay. Okay. Now, let's take a look at bag of. Okay, we have one assignment tonight that uses bag of. So let's see what bag of. Bag of XPL. So L is a list of all the objects X such that goal P is satisfied. Now let's think about that. So there's 3 things. Are you with me? And the main thing is, what is P? It is a what? It is a goal. Is everybody with me on that? This P is a goal. All right? So, what is L? L is a list of all the objects X. So what is X going to be? X is going to be all the objects that satisfy P. It's going to put them in list L. All right? That's the idea. So check this out. When we said age child 5, right? When we said age child 5, what did that give us? When we said age child 5, what did that give us? Boom, 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 boom. Are you with me? That gave us this. These were all the ages that satisfied that. Yeah? Okay? So, what do you suppose bag of this is going to give us? What is that going to give us? Yes, it's a list of all the objects. So it's a list of all the what? Of all the child. And so here, because child matched and, right, so it's going to be a list of all the, yeah, and so you're exactly right. And Tom, Henry. Does everybody see how bag of works? Okay. How about this? Can we predict this one? Bag of. Capital A age. And then age, Pat age list. So now what will this be? Isn't this a great example? So it's a bag of capital A age such that what? This goal is satisfied, and then it's the list of all those. So what will this be? Anyone want to? Oh, right. Because Pat, oh, yeah, it's only going to succeed for Pat. You're right. So it's the list with 8 in it. Right. Okay. And now, how about this? So now what's this one going to be? What do you think? It's the list of all the what? Child such that, oh yeah, such that the age is anything. Right. So it's going to be the list of all the children. Exactly. Are we good? Oh, there's more. Oh, there is more. You're right. Oh, there is more because, yeah, of any age. So age 5, and then there's the list of 5, and oh yeah, that's good. Are we good? Okay, so I have given you a homework assignment that uses bag of to do permutations, but I gave a pretty detailed rundown of how to do that. So I hope you can work through that tonight. Are we good?